Check. Thank you, Ray, for the kind introduction. I'm Aldo Raeliarijaona from Carnegie Institution for Science, and I'm going to present a story about stabilization of ferroelectricity in Hafnia with epitaxial strain and electric field. In the beginning, I'd like to acknowledge my supervisor, Dr. Ron Cohen, the funding agency, ONR, and the computation facility, the HPCMP. So to begin, let me first start off with the motivation of studying ferroelectricity again, preaching to the choir, but ferroelectric films have several applications from dynamic random access memories to what we would like Holy Grail, the non-volatile ferroelectric random access memories, and other actuators and sensors. But when you go to lower sizes, sizes, regular ferroelectric materials encounter some bottlenecks because we have the polarizing field which quenches polarization, so you lose all those benefits of the non-zero spontaneous polarization. Then in comes Hafnia, which has a robust ferroelectricity at the nanoscale, and it is also compatible with silicon. So it has this promise of being very ubiquitous in future electronic devices. I'm gonna go through a short background, and you've seen this from the earlier presentation of the phase diagram, temperature and pressure of Hafnia. At high temperature, we have tetragonal, so of about 1800 degrees Celsius. Then if you lower it to room temperature all the way to 0, we see monoclinic phase or the Baddeley phase. And if you increase pressure, going to the right, you have the PBCA, and if you increase it furthermore, you have you find the PNMA structure. So nowhere in this temperature pressure phase diagram do we see a ferroelectric or polar phase. Then came several studies which show that the ferroelectric phase here, the relevance phase, it's a PCA2 sub 1, it is metastable. Meaning, if we can actually drive the system from whatever state we have, let's say PPTA, through the barrier to the PTA2 sub 1, through ferroelectric, through electric field applications or strain, then we'd expect a ferroelectric phase to be stable. Additionally, there's such a thing called the wake-up effect in Hafnia, where Hafnia sample needs to be, let's say, given a wake-up call first. So you need to cycle, to go through some cycling of electric field to bring the polarization to a larger value, the remnant polarization here shown at. So this wake-up effect usually is attributed to the defect migration, which means if we'd like to reduce this cycling so that we do not get a premature fatigue on our material. So the story I'd like to tell with this presentation is that of a stabilization with electric field and strain. Since we're talking about orthorhombic phase, let me first start with how to lay out an orthorhombic unit cell epitaxially. So we have three different kind of a scenario where if the lattice constants were close enough, we can actually lay them on a square and apply a biaxial strain. Or if it is totally mismatched, or then we can consider two different cases, such as B and C, where it's either one of the short axis is in registry with one lattice constant, or the long axis is in the diagonal. We use first principles computation, and mainly with the GPRB pseudopotentials. We apply strain by restricting the epitaxial, by constraining the epitaxial lattice constant to a certain value, and we allow the out-of-plane lattice constant to relax, and also the atomic position. Performing those calculations, we found we considered three different orientations: the 001. So the Z direction is out of plane, for panel A. The B it's the 010, and C it's the 100. First, depending on the most stable state is the Baddeleyite. This confirms experimental observation. But depending on the epitaxial strain that you apply, you can actually stabilize, for instance, the PMN2/1 phase at PMN2/1 phase at when you actually uniaxially strain it, or the orthorhombic PPCA. Here we'd like to focus on the 010 oriented film, starting with the PPCN, and at an epitaxial lattice constant, which is 5.14 angstrom. This is the lattice, approximately the lattice constant of yttrium stabilized zirconia. And toward the end, I'm going to tell you the reason why we chose the PPCN. But let's just say we start from the 010 oriented PPCN, apply strain in plane and the electric field out of plane. We apply the electric field through constraining the forces on the atoms. And we starting with the PPCN, we gradually increase the electric field from 0, going to 1000 megavolt per meter, and then coming back down all the way to 0 again. Doing so, we plotted the electric enthalpy, the internal energy, the polarization, and the out-of-plane lattice constant. We see a phase transition occurring, driven by the electric field, occurring around 150 kilovolt per meter. So this is kind of an order of magnitude smaller than what is used in a wake-up effect experiment. And so as we drive as we increase the magnitude of the electric field, this ferroelectric phase stabilizes even more. And then as we decrease it, it stays at the PCA2/1 phase, all the way to whenever the electric field is turned off. We looked at other orientation, the 100 here. We see a similar case, but this time the electric field is much larger for the transition, that is. Here it's at 250 megavolt per meter. And for the 001 oriented PPCN, it's around like 1000 megavolt per meter. But the same story goes. You start with a PPCN. This is different from what Hugo Aramberi and I think Jorge Iniguez, they start with the PBCM phase. But we start with the PBCN, we apply the electric field, we see a phase transition, and then we take the electric field off. It remains polar. Then we ask the questions, what happens if you take off the strain, so just relax everything. We did so, and when you relax everything and still apply the electric field out of along the same direction, which is the crystallographic P here, then up until a reasonable, let's say 500 megavolt per meter, and then when you decrease the electric field, it goes back to the same path, back to the PBCN phase. So this tells us that key in stabilizing the ferroelectric phase in Hafnia are the epitaxial strain and the electric field. It's their combined action that actually help in the stabilization. Now I come to the story, I guess, of why we start with the PBCN. So Professor Karen Rabe actually brought a very good point earlier in her presentation of the polar of a zone of soft mode of driven phase transition in Hafnia. Here, when you start, let's say with a tetragonal phase from, let's say, 2000 degrees Celsius, and then constrain the or applies epitaxial strain. So when you expand, for instance, tetragonal, you will see all these soft mode pop up all across the Brillouin zone. The endpoint, the soft mode at endpoint will lead you to that PBCN phase. And if you do a group-subgroup relationship analysis of the PBCN phase, from there, the endpoint, you combine it with a gamma 2 plus, you get the monoclinic. From the endpoint, you combine it with the gamma 5 minus, you get the PCA2 sub 1 phase. And so, and even for the tetragonal, if you focus just on the gamma minus, gamma zone center phonon, you can also get the other polar PMN2 sub 1 if you freeze in the gamma 5 minus soft phonon. So if, let's say, you start at tetragonal, freezing the M distortion, you get the PBCN. Now, if you apply an electric field, then you drive it to the PCA2 sub 1 phase. So I hope that my presentation has convinced you that this actually, we can see this continuous phase transition from the PBCN to PCA2 sub 1, driven by electric field and epitaxial strain. And with an adequate film orientation, you can actually have a relatively efficient phase transition here with a small electric field. Thank you.
Thank you very much.
Yes. Huh? Uh-huh. Yes. The gamma point? Yes, it's polar. It will lead you to the PMN sub 1, the different. But then what you do so then so with the PCA2 to 1, you have to have the N and the gamma 5. Yes.